I built a new CNC router with a fixed gantry, which is extremely rigid. The design is ideal for watchmakers, knife makers, scale modelers, and hobbyists who like to mill aluminium, brass, and steel. I make again a build series, and this is part 1, where I give an overview about the specifications and explain the design in detail. Hello and welcome to my channel. Since quite some time now, I offer the part kits for my Watchmaker design. One of the first to build it was Mike from AW Labs. Mike is an independent watchmaker out of Washington, D.C. in the US. He designs and makes awesome limited edition wristwatches, and most of the parts, especially the stainless steel housings, are milled on the Watchmaker. Since shipping a completely assembled machine into the US was a tariff gamble at the time, Mike just got the machine parts and assembled the machine by himself, using the parts I have specified. The base design was customized because the prerequisition and challenge was to fit the machine into his existing enclosure, a leftover from a failed Kickstarter CNC which didn't meet his expectations. Please check out his social media channels. He creates truly some pieces of art. I put the links in the description below. The machine that I will build now goes to a university in Switzerland. It's a full-blown build, including the enclosure and CNC controller, and a ton of accessories. Let's have a look at the specifications. The work area is 520 by 420 by 170 mm, with a slightly larger travel so the tool setter can be placed outside of the machining table. As always, I use a spindle from Spinergy, this time a water-cooled X22 with 2.2 kW, 30k RPM and an SK20 interface. The rapid feeds of this router go up to 22.5 meters per minute. The overall footprint is 1550 by 1250 by 2140 millimeter, and the machine weight is approximately 900 kilo, most likely more because I have not assigned a weight to each and every component in the enclosure and the controllers. The power requirements are 230 volt with 2 separate 16 amp fuses. The bolt screws are from TBI with a 60 mm diameter and a 5 mm pitch. They are ground to C5 precision and have a preloaded double nut with 0 backlash. The bolt screw bearing housings are from SICK with high quality NSK bearings. Linear guides are from Highwin with size 20 on the gantry and Z-axis and 25 on the machine bed. All the blocks have a medium preload and additional seals, which I explain later. Axis motors are AC servos from Delta with 400 watt, the one on the Z-axis with an integrated brake. In combination with the fine-pitch bolt screws, they allow a resolution of 1 micron on each axis despite the high rapids of 22.5 meters per minute. The Z-axis uses a belt and pulley system from Gates. I know that some people have reservations about timing belts, but these are completely unfounded if you use the right components. The drag chains are closed tubes from Egos. They prevent chips from getting into the chains, and as always on my builds, you will not see a single exposed cable in the entire enclosure. Overall, the Watchmaker is a very versatile design, which can be easily adapted to the customer needs. It is scalable in 50 mm increments from 300 by 250 to 500 by 400 mm work area. Spindle, axis motors, and bolt screws can be adapted in quality depending on customer needs. The machining table is highly customizable for all sorts of work holding, like vacuum tables, regular and modular vices, zero clamping systems, and so on. Whatever you need is possible. This time the customer decided on a complete machine, including an enclosure. I went with the machine cabin system from Etam, which is easily to expand and adaptable to different sizes. It has a large folding door for complete access to the machine, a large side window, a chip tray for easy chip removal, which could as well be redesigned for flat cooling, and accessory compartments, in this case for the spindle cooling and vacuum pump. The heavy-duty casters guarantee a secure stand, but also an easy way to move the machine around because the customer might relocate it between different shops in the same building. There are several steel cabinets from Rittal directly attached to the machine. The CNC controller is based on an Eding CNC 7060 board and houses as well the servo drivers, safety relays, ATC relays, and so on. There are dedicated cabinets for the spindle and pump VFDs and the ATC pneumatics. And finally a small one for the MQL pump controller and a few control elements. So much for the overall specs. Now let's have a closer look to the actual machine design. It is a bed slinger design with a moving table and a fixed gantry. This is a good compromise between a classic VMC and a router with a moving gantry because it offers the same rigidity as the VMC but with higher wide travel of the gantry style router. The benefit of a fixed gantry is that it allows for a very stiff design, which is good for precise and shatter-free milling. The demerit of the moving table, however, is that it requires twice the wide travel in overall machine depth, so to still keep a reasonable footprint, there are some limitations. Also, another issue to consider is that the larger the machine table, the larger means heavier are potentially the workpieces. But a huge difference in weight of the moving table might cause issues with the servo tuning, which is a function of the load to inertia ratio. But the same issues exist in a VMC and are even worse, because here you also need twice the machining area in X, and in Y you have to add the depth of the column to the footprint. That's why this design has the best footprint to stiffness ratio for small-sized machines. The main feature of my design is the large base plate made out of solid aluminium. It has a weight of approximately 100 kilo and is the solid foundations for all other parts. The reason why I decided for aluminium instead of a mineral cast or UHPC base, despite its inferior damping properties, is that I wanted the machine to be easily scalable. Many people I talk with have different requirements in work area or limitations in footprint. With this design, I can offer theoretically a total of 20 different sizes, which is simply not possible with a casted base. There is no need for mold making, no mess with molding, no need to level the mounting surfaces. Every function and mounting surface is already milled straight into the base. The gantry is built out of heavy aluminium extrusions with 160 by 80 mm profile, which are filled with epoxy granite to reduce vibrations. They are reinforced with 20 mm thick plates on the top and front for mounting the rails and ball screws. The profile slots are intentionally inclined slightly inwards to increase the preload of the screw connections and are therefore not particularly suitable for direct mounting of the rails. And the slot reduces the mounting surface anyway, so adding rails directly to extruded profiles is a rather poor design. The Z-axis is again a sturdy box design with fixed rails and moving blocks. The benefit of this design I have already explained in one of my previous videos, which I link in the description below. An issue of the moving bed design are the exposed rails and ball screws on the bed. I have seen some solutions with a rolling foil or worse with bellows to cover the exposed area. A rolling foil is an interesting design, but it requires some space in the front and back of the machine for the foil to fold, depending on the position of the bed. Or alternatively, a free space under the machine in case it is a one-piece foil connected to the front and rear of the table. In any case, this adds complexity and the chips are dumped in this area, so some extra space is required there. A very poor design is to add bellows. When you do some serious machining with larger sized chips, the bellows are filled immediately with the chips and don't compress anymore. And when you create smaller chips, either because the machine is not capable or you do stuff like thread milling, these small chips have the habit to adhere as a nasty smear to the fabric, especially when you use an MQL. And the flimsy bellows are almost impossible to clean with a shop vac. Everyone who ever tried that knows what I'm talking about. I have used fixed gantry router for a couple of years, and in my experience, the best and easiest solution is to protect the ball screw with a fixed cover and to use extra seals on the linear blocks. Hyven offers a large variety of add-on seals for all sorts of exposure, from nasty, abrasive, fine particle MDF dust to metal chips and even weld spatter, like on plasma cutters. I use the appropriate seals on all of my machines, regardless of the design, and so far I never ever had to replace a faulty block. So much for the brief design overview. Please let me know in the comments below what you think about the machine. The next video will show the milling and assembly of the machine. The other videos will cover the enclosure and the control cabinets and the first test cuts before delivery. If you don't want to miss that, subscribe to the channel and hit the notification bell. Also, please give this video a thumbs up if you like it. Stay tuned and see you next.